Welcome to Build with Naz. I'm Naz. I'm the author of the Rebel Open Core repo and developerlife.com developer website, which I've been running for quite a few decades now. This video, this live coding section, is related to the Explore Linux TTY process signals part 1 video, which is contains a lot of background information. This video will go through the details of sending and receiving signals in Rust and also managing processes with a lot of control. So we can spawn child processes, do things with their standard in, standard out, standard error with IPC using the procspawn crate, and also use both Tokio and signal hook to send and receive signals, so we can essentially manage either raising or receiving POSIX signals from the operating system or via the operating system from other processes. So with that said, let's get started with this live coding section. So this video, part 2, will only contain sending and receiving signals in Rust. Part 3, which is the next one, will be all about manipulating commands, Tokio process commands, essentially async commands in Rust. So we'll be able to create things like asynchronous shells, REPLs, and have much greater control over external processes that we run using command. So we talked about signals earlier, and now we're going to transition from like how things work in POSIX to like how these things can be manipulated in Rust. So we're going from like the theory and knowledge, not even theory, we're going from the knowledge and using tools like the shells and other programs to actually see these behaviors, to actually doing it in Rust using system calls. So for the first example, actually before I start that, let me create so I just created a new crate called TTY, and I am going to open that here. And actually, before we get started, I do need to put some dependencies in there. Just let's see, these are, I'll walk through why we need these dependencies as they come up, but I just wanted to put them there to kind of get started. So the first thing we're going to do is, in the realm of sending and receiving signals, we're going to do the first example is going to be creating a program that can register a signal handler and then do something when it gets that signal. And for that, we're going to be using Tokio. I wasn't aware of this, but Tokio has support in it for simply, asynchronously attaching an asynchronous listener for signals. So let me see. Let's that'll be our first example. So let's do this. We're gonna have a entry in our cargo toml for this thing, receive signal, and so let's go make this file. Let's see. So there we go. All right. So in receive signal, one thing to note is that with this is nothing to do with Tokio, but there's certain signals that we cannot work with. Like so, for example, let me give an example of this. This is something that I found out while I was making this. So this is just documentation. So essentially, we have, this is the POSIX. Okay, so there's a built-in thing in Tokio called Control C in the Tokio signal module, and that's used to respond to the user pressing Control C in the terminal. So I mean, not terminal, but essentially in the process that's that this is used in. So this is an example of that. So you can basically create a stream and then the signal kind is actually this, let's see, this is, why is this not here? It's Tokyo. Actually, let me do this real quick. So let's make a async main function. Let's do this, Tokyo main, and then async. And here we're going to return a get result containing the unit type, and oops, and then we just do to. Okay. So there we go. And then let's see if here. There we go. So let's look at the control C. So this is the in the Tokyo crate itself. So this happens when a control C notification is sent to the process. So this is when the process itself gets a control C signal through the operating system or whatever the means. This particular the code that you write will actually run. So actually this is a bug in Rust Analyzer. If you put like if there's this hash Tokyo main, this macro, then it turns off the syntax highlighting. This is very strange. So actually, I guess one thing we could do is quite simply replace this with a doc comment. Let's see if that, yep, that fixed it. All right, so let's see. Okay. Okay, so here we have the way that it would work is that we create this in Tokyo, like the signals are all actually in this actually I should probably open this in docs.rs for Tokyo, and then this might be easier too. Yeah, so let's look at signal kind, and this is much better. So here actually we can see that there's let's see, where are these are the constants. So essentially we're calling something called signal kind terminate, and if you look here, terminate, this function returns the sigterm signal. So it's just an abstraction. So in other words, this is the sigterm signal. So this is saying to use the signal, let's see, signal function, this one. So this what happens is we can create a new listener which will receive notifications when the current process receives the specified type of signal. So the specified type of signal here is sigint, and this is the essentially we're telling this signal function, hey, when you get one of these, I want to know about it. So this actually creates a signal which essentially behaves just like an asynchronous stream. So you can just call receive on it. It's like actually more like a channel. You could think of it as a stream as a channel. Like if it was a stream, you could call next on it. But this is receive, so it's more like a channel, but more like a one-shot channel. So essentially, you create one of these. You can think of it as like it makes a channel, and then you can use it in a Tokyo select block, and then call the receive function on it. And when you do, and somebody presses Control C, or you say kill-9 and you type in the PID of the process that's got this code in it, then when the sigterm is sent using the kill binary or using the something like a task manager, like this thing, system monitor, or if you use like btop or htop, you can just pick the PID of a particular process and just send the kill to it, or yeah. So that's an example, or actually sigterm, so not kill, but the other one. So then that would be the equivalent of pressing Control C or sending a Control C, which is the sigint, I think. If we look here, where'd it go? This is signal kind. Yeah, pretty sure it's sigint. There's terminate. Oh, sig term. So not SIGINT. Okay, so it would be terminate. So it would be essentially it'd be kill-9. Or you could just in the GNOME, in this case, like the system monitor, you would pick this and just say kill or terminate. Actually, it'd probably terminate. I wonder, sig term. Is there a sig kill? Oh, I think sig term is the kill signal. Pretty sure. Yeah. Actually, we can. It's in this. In here, what sig term is, so there's no need to guess. So we have sig int, sig quit, sig pipe, sig stop. Where's sig term? Oh, not in here. Okay. Interesting. Sig term. Guess we can Google it. So, term versus sig kill. That's right. Let's see what the difference is. Sig term is a signal used for terminating a program. Okay. And sig term, you can do kill. Okay. That just a sig term. Oh, sig kill is -9. I see. Got it. So sig term and sig kill. So kill -9 is sig kill. Sig term is just like, that's why there's a distinction here. If you right click on a process, you can say kill or terminate. This is sig term. Kill is like a much harsher way of doing it. So sig term, basically if we say terminate or sig term, then in our made up example, this piece of code would run before the and then we could decide here what to do with the we could probably just exit the process or do something that makes sense. There's some limitations actually as to which of these signals you can actually listen for. So one of the ones that you cannot listen for is sig stop. So this is actually let's see. This is actually a limitation of the Linux kernel itself. So so we can't override sig kill or sig stop. So interesting. So sig stop. Oh, interesting. So there's sig stop. As you can see, it's pretty complicated. Like what all these different. Let's see, sig stop. Yeah, this doesn't even have sig stop or sig. Let's say kill. Okay, that makes sense. So okay, this create signal hook, which we'll be using in the next example, actually has it's far more sophisticated than the stuff that comes out of the box with Tokio. And so if we wanted to do any kind of like sophisticated signal processing or signal handling, this is a better crate to go with. Yeah. So regardless of what these APIs expose, like ultimately there are syscalls that get made, and if those syscalls don't necessarily support whatever it is that we want, then it's not going to work. Let's see. Oh, this is actually another good example. This is also from the signal hook. So these signals are forbidden. So like sigil, sig FPE, sig segment, SEGV. So yeah, these are all like limitations of the underlying OS. So okay, so with all those sort of details around what we can't do, let's look at what we can do. So let's say we want to register, and this happens all the time with not all the time. In TUI apps, they have to be responsive in the sense that when the bounds of the terminal in which the text user interface app is running, when it's resized or changed, then it should repaint itself. And one way to essentially register a hook for these kinds of window resize events is to use a signal handler. So so let's say that in this case we would want to do, and actually this I think it's called sig, I think window change or something. Let's see, there it is, window change. That's it. So so let's grab the signal first. So let's do this. Do OK. Let's import this. Utils core. It's just a macro that makes it slightly easier to. I don't know why this isn't. Okay. Okay. And OK. So there we go. I don't know why it didn't automatically import that. So this is just a little macro for just a little macro, so I don't have to type OK like this. Something like that. Oops. This automatic parentheses and brace completion is causing some issues. So let's do this. Let's make a stream. Actually, it's not a stream because stream would have, let's call it channel. Oh, actually, this is a stream. Well, let me see what the docs say. Let's see. So we want the signal function. Let's see, signal. There it is. Oh, it just returns a result which has a signal in it. And that is just a listener. Listener can be turned into a stream using signal stream. Okay, so it is a stream. Oh, infinite stream. Okay, so stream it is. So what we're going to do is we're going to name this thing a stream of sig. I think it was W. What is it? Signal kind. I think it was change window change. There it is. Sig winch. Okay, sig winch. And then here we're going to say. Let's see that. So we're importing like that Unix signal kind. Or actually, do I want to leave Unix prefix there? Why not? So here we have the function that creates the stream, and then here we have the actual signal. So if we wanted to break it out and say signal type that we're interested in is this one. So the signal and the stream. And we can do signal here. Okay, I think this is a little bit more readable. Where yeah, that makes sense. Let me update the. Let's see. So we got stream. Oh, let's see. Oops, maybe. Let's see. Let's do this. I think. Let's see. I'm updating the source code that I am going to publish in this repo as well. So as we're doing this, okay. All right, so here we have our signal that we're interested in, and this is the stream. So this is an async stream, and so in order to use it, we have to do something like this. We can say loop, and oops, and in the loop we can say that's it. So, and oh, this loop never actually loops. Oh, right, because it's just a one shot. So basically what it's saying is that we could have just written this and it does the same thing. And then when you need a break. So I'm going to roll all that back. We're going to do, we are going to have, this is just the one branch. This is the, this is got a signal for change, for window change. So window change, so it's not got a signal, say respond to window change signal. So just like we can respond to window change signal, we can also do things like Control-C handling here. So we can do, this is an easy one, respond to Control-C signal, because Tokio provides that out of the box as well. So here we can see Control-C right there. And so this is a stream that it generates that we can just instantiate and use. So this is actually, let's see. Yeah. So these are Control-C notifications, and this is the stream, not that one. Okay. So this is sort of a nice, nice facility that we have provided by Tokio. Let's see, what is the problem? Oh yeah, right, we have to put a loop here. And then there we go. All right. And now it's complaining that these are all not looping. So one thing I want to do is that I want a, let's say I want a timer, an interval that runs every 500 milliseconds. So I want an interval which runs, oops, Tokyo time. Why isn't it auto-completing? Yes. And I want it to take like every half a second. So let's do this. Every half a second it's going to tick, and what I'm going to do is, this is respond to tick, or I should say run at each tick. Let's see, tick interval, and there we go. Something like that, where we're just saying tick. So it's just, now the errors go with the loop because this will loop. So here I can just add this to the workspace settings. It's a spell checker. Okay, so we have the signal, we have the stream that we can basically use to get notified when the signal is received. And also we added this Control-C handler thing that's provided by Tokio. So finally, if we run this program right now, it'll just go on forever. Let's see, let's run it and see what happens. Building, let's see. Still building. Okay, so it's ticking. Now if I actually change the window size, how do I do that? Can I split this? Oh yeah, I can do this. Maybe I can put it here and put this to the side. There we go. So sig win ch receive. So let's do this. Instead of running it here, let's do this in a terminal. So we're going to do cargo run, and we're going to cargo run. Let's see, cargo run, and there it is. Tick tick tick, and I can actually just very quickly change the. That's one way to change the window size. Let's run it again. So there you go. Every time the window gets resized, it exits. So another thing I might want to do, so that works. That's this thing working. And then let's say that, oops, unfortunately Rust format doesn't work inside of this select macro, because when this thing expands, it's just a stream of tokens that the formatter doesn't know what to do with. So let's do this. Let's do cargo run, because this is the only binary, that's why this is working. If I hit Control C, notice that it says Control C received. So what happened was Tokio provides a facility for us to register for the Control C signal handler. So if I run this, let's see, how do I get the PID? How to get PID of the current process in Rust. Let's see how this. I have a way to do this, but let's see if this. That's easy. So let's do this. Let's print the PID first. So if I do cargo run. So here we have the PID. So if I spawn another terminal here and I say kill, and then let's say I put kill help. I don't know the number, the signal number for Control C. Let's see. You know what? This is. We can just hit Control C. I was gonna send a signal from the kill program, but that's too much work. Let's just let's see. I guess we could do this. We could say kill-L. So let's see. We got hang up, interrupt, quit. What do I want? 9 is kill. I think Control C would be 3, I think. So we can do it like this, and we can say kill-3, and then we can grab this PID. Oops, no. So the PID is this one. Let's see if that worked. Oh, that got a sig quit, so that wasn't it. We want a different one. So there's number 28, WinCH. Let's do that. Let's do this. So our PID is, oops, I hit Control C. Dang it. Let's do this. Okay. So let's do, instead of kill signal number 3, let's try 28. There you go. So sig win received, window change. And then wondering which one is sig term. There you go. That's the one. So let's do that. We'll do kill, and the PID is this. Oops. And let's do that. And then, so it's ticking, and then I want to do 15. So I do sig term. Sig term. So, oops, sig term. Which Control C is which? Sig int. Ugh, okay. Where's int? Oh, 2. Okay, let's do this one more time. So now I have the PID. So here we have kill-2. Boom. Control C received. So this is kind of handy. So kill-L will give a, I should put that in here. So let's see. What we can do here is that, let's see, sending signals to the process. So here we can use all the signals we can send. You can run the following command, which is, I think we can do kill-L, and then to send Control C to the process, we can run, let's see, yep, PID, and oops, and then we got, actually we can just do -3, or actually we can do, actually does that work? I wonder. Kill-int, let's do that. Let's see, int. I know this PID doesn't exist, so yep, that works. So we can do kill-int. That works too. And then to send, I think it's window. I think it's winch or something. Sig winch to send. Let's see, Control C, which is the sig int, I think. Pretty sure. SIGINT. Yeah, SIGINT. Oh, okay, it's not listed here. Oh, interrupt. Okay. SIGINT. And actually, that's interrupts, and this is from. Let's see. This is signal kind, and then interrupt. So we can say send SIGINT. Control C, which is SIGINT, which is also Tokyo signal. We got Tokyo signal. What is it? Unix signal. Oops, and then I think we got a bunch of functions here. Nope, interrupt. There it is. So interrupt. Why is that? Oh, because that's not what. Where's interrupt? Is this not? Oh, signal kind. Oh, okay, so signal kind. There we go. So we can send SIGINT, which is Control C, and then aka this thing. So we can run like that, and then to send SIGWinch, and then here we can say aka window change the process. Simply change the terminal window size of the process running in, or run the following command. And this one is using I think it's kill minus 28. Yep, 28, which I think was 28 was WinCH. Okay, WinCH. So, and that's another way. There we go. And let's do this. Okay, so here we have the first example where we're simply running it, and yeah. So now let's say I want to terminate this example because I don't want to keep it running for a long time. Let's say if nobody has changed the window size or received a Control C, I want this process to self-terminate. So I can do it this way. I can say sleep future is Tokyo sleep, and in 5 seconds, let's say. So in order to use this, I have to pin it, and I have a whole video for pin and box explaining why we need to do this, and I have another video on async Rust also explaining why this is necessary. But future is just a data structure in Rust, and so it doesn't do anything until you call .await on it, and the executor makes progress on it. And so this entire thing gets unwound into a state machine, which actually contains stateful. It's stateful, and so we pin it so that we cannot, it can't be moved once we create it here. Otherwise, the semantics don't match up with what we think sleep should be doing. So, and the pin and box video that I created on the channel. Let's see, where is it? Oh, I just realized. Oh, here we go. Developer life, and then where's the channel? Yeah, so it's where is it? This one, the box and pin. This one has a whole lot more information in it about this kind of thing. So okay, let's do this. So we can do. If you haven't already, please subscribe to the YouTube channel, and also sign up for our updates. We have a newsletter I send out every time I create new content. So it's not much. It's maybe you'll get like maybe 1 to 2 a month, something along the lines, depending on how often I make content. Okay, so let's do this. So we're going to sleep for 5 seconds and terminate the program. So terminate the program if running. So here we can say like that. It's more like slept for, not sleeping. And now when we run it, what we can do is you'll see it's ticking, 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 and after 5 seconds of this, it'll just essentially terminate itself. So there you go. And we can also terminate anytime by doing this. We can terminate it by pressing Control-C. We can also terminate it by using using the PID. We can just grab all kinds of different, let's see, kill int, so that'll do Control-C on it. Oops, oh, that was unfortunate. Oh, because now it has a 5-second timeout, so oops, so that won't be so quick anymore. All right, so yeah, there's our very first example. And then let's see, yeah, one thing we might actually want to add to this example is the ability to copy the PID that's generated into the clipboard, because you know, for just convenience. This actually sets up a nice example in procspawn later on. So let's do this. In order to access the clipboard, we need the CLI clipboard crate, and I'm actually on Ubuntu 24.04 running Wayland, and so there are some strange behaviors that happen when using this. So let's say that the number of lines of code is actually pretty straightforward to get this to work. It's let's see, import for this one, yeah. So this essentially, when we run it, we should be able to see the let's do this. Let's set this up. So let's say kill, interrupt, and then we'll get this ready. So if we say cargo run, now if we say paste, you see that the PID was 5, whatever it is, 36, and I pasted it. So I was able to paste it. This actually copied correctly, but notice this strange warning. So this warning, I did some research, and this comes from Wayland and the Mesa drivers on the open source, because I have an AMD graphics card. The Mesa drivers for my graphics card, apparently along with Wayland, are generating this message, and this is being piped to standard error. So this is something that this particular process, no matter what I do, I can't really, let's say, take the standard error and pipe it to null. So and so I'll get the strange error message, even though, you know, it's working. This is a warning from a Mesa driver. So in the procspawn example, which is one of the last examples, I'll actually show how to get rid of this by spawning a different process to do this clipboard copy. And actually there's this is the sort of the simpler way to do it. A more sort of the code that's a little bit let's say not cleaner. This actually works the same in procspawn as well as here, so I'm going to end up probably just using this. Let's see if this works. Let's see, and again, a lot of this is due to some Wayland teething issues. Hopefully it'll be resolved in the future. But yeah, for now it gives us a nice excuse to use basically to use this procspawn crate to spawn a process to copy something to the clipboard. It's a bit made up, but we can get rid of this warning using that approach. So yeah, with that, that's the end of example 1. So when we did the example and we copied the PID to the clipboard, there was a strange warning message that showed up, and we don't really have any control over suppressing that warning message because it comes out to standard out from some Mesa driver in the Linux kernel. So since this, in order to copy the PID to the clipboard, the crate that we are using, which I think under the hood uses, I think, let's see, I think it's like Rust, basically the Wayland Rust implement crate. So I think I have it written down somewhere. I can mention it a little bit later. But so under it, like the, let's see, I think CLI clipboard ends up using. Where is this? So here it uses the X11 and Wayland. Nope, that's not it. Let's look at this real quick. Here it is, wl-clipboard-rs. This is the one that's used, and this is for programs that don't spawn a window. So it's essentially terminal-based applications. So a process that doesn't have a window, so it doesn't use something like winit. So what happens is that when this code runs, it ends up dumping this warning message, and that warning message pollutes the standard out of this process. And this is a problem if we are talking about CLI and TUI apps that run in raw mode, or just in general, polluting output is it's not desired. So one way in which we could actually sort of get rid of this is using this crate called procspawn. So procspawn is a crate that is used to, it's kind of like, there's a standard library equivalent of this where you could just spawn a process, a child process, with the same exact executable as the currently running process, that ends up just respawning it with the same arguments that were passed in the command line. Procspawn is far more sophisticated than that, because we can almost think of it as like the mental model or the programming model is very similar to Tokio, where it's kind of like thread spawn, and so or Tokio task spawn. So basically like Tokio spawn or a standard library spawn. It's very similar to that, where you can just call the procspawn spawn function and then pass it some data, and then this part, it runs in the parent process, and then this part runs in the child process, which is really cool. And then you get a join handle, which you can use to wait for this child process to complete and get any results. So if there's any results that get returned or panics, they'll be serialized and sent over. So this is really, really cool. Crate, and it also works with IPC channels, so that you can kind of do something very similar to broadcast channels or MPSC channels that we're used to with Tokio. But again, this is completely synchronous code. This is not async. There's no Tokio executor, and all the serialization that happens using the bin code crate, not the JSON stuff. So this is pretty cool. Bin code is a nice crate as well. So let's see. I think platform support. Yeah, it's only Mac OS and Linux, not Windows, which is fine, because all the stuff I'm doing is in Ubuntu 24 anyway. So let's see. Okay, so let's see if we can do a version of this where we spawn a child process, and then we grab the PID of that child process and put that in the clipboard, which is kind of cool. Similar to what we're doing here, but minus the Tokio stuff. So this is a bit of a like exploration of procspawn. And then I have another example of procspawn where we can mimic this kind of like, not mimic, straight up use channels. But these channels they span process boundaries, which is pretty amazing. But to use them, you wouldn't even know. It looks almost exactly like quote unquote normal code running in the same process. So okay, so let's see, with that, let's go grab some dependencies. I think we're gonna need, let's see, I think we have procspawn. Yeah, so we just need IPC channel, not for this particular example, but the one after that, so might as well just add them all at once. And then we need to add a bin target for procspawn. Let me do that. And so here we will need procspawn. There we go. And let's see. So let's add some comments here real quick. So procspawn, this is not going to be using Tokio. This is just straight up using normal synchronous Rust. So I'll just do main function that doesn't return anything, and then what we'll do in this main function is, so let's see, procspawn, this is just getting rid of these spelling errors. Here we go. Okay, So the pattern is very similar to spawn. You spawn something, except that, as you see in the example, the data gets passed across process boundaries. So the actual data, the arguments are on, let's say, the parent process, and when you spawn a new process that's a child process, those arguments actually get serialized using bin code sent across the process boundary to the child process, and then that deserializes it and then uses it, does some work in a child process, and then returns the results. If it panics, that panic is also returned. So that's pretty cool. And of course, any errors as well. Oh yeah, and it can return results which are not panics or errors, and those can be retrieved using the join handle. And we can also grab the standard in and standard out of the child process, which is how we're going to suppress the warning output when we go to copy something from the clipboard. So essentially we're just going to spawn a child process, and then its PID is going to be copied to the clipboard. But because we're going to be spawning something with procspawn, and for the child process we're going to mute the standard error, then we won't see that warning message basically. So the first thing you do in a procspawn function when you use procspawn is that you have to basically tell it, essentially you have to call this init function, and any lines of code before the init function will be executed again when you spawn. So I basically put as the first line of the main function. So I don't want this kind of makes sense when you see the rest of the code, but so let's grab the it's recursive because it's going to spawn this process again, but it's going to give it different arguments, and then based on the logic, essentially you can think of it this way: this is like before each. So any code that you put in here is like before each. Like if you think about a test, all the code will be executed every single process that's spawned will execute this, if we have anything there, but we don't, so we're just going to leave it for now. So and if you don't add this, procspawn will generate a compiler error, which is really nice. So let's grab, we're going to get the parent ID, so now that's in PID. So then what we're going to do is we're going to make a function. So if we look at procspawn channel, oops, not channel, spawn, where is it? Here it is. So you can kind of see the template for this thing. You do the init, you make arguments in the parent process, and then you spawn it with the arguments, and then over here we're going to get those arguments as parameters to this closure running in the child process, which is pretty awesome. And then what we can do is, let's go look at the builder. Yeah, there we go. Not cool. I think it's just procspawn builder. Yeah, I think it's just procspawn builder, this one. So this is where we can manipulate environment variables, and we can also manipulate the standard in, standard out. So here's where we're going to basically mess with the standard error of the child process, where we're going to copy the PID of the child process into the clipboard. And because we're going to do it in the child process, we will see nothing in the terminal of the parent process. It's a bit of a made-up example, but it's kind of cool to see we can do this. So we do get builder, and this will return a procspawn. What will it return? Procspawn builder. We were just looking at the docs for that just now. So here we do and let's see. We will create a new builder with standard out. Actually, standard error. That's null. And actually, with standard as null and standard out, that's byte. So we're gonna essentially control what happens in this builder. So let's see. So we do let mute it equals. So we do new builder. Then we say standard error is not procspawn. This is just standard process standard IO null. Then we say we pipe the standard out. That means it won't come out to the standard out of the parent process. This is going to be in a data structure. This will be nothing, so we're suppressing. This is suppress standard error, and this is capture standard out. Yep. So this is not going to be dumped into our terminal, the parent terminal. The dev PTS won't see it. And let's just return it. And then what we can do is the way this works is that we do something like let's see, we do okay, let's go make the thing that we're gonna run. So we're gonna make a function. We're gonna say, let's see, this function executed in a separate child process. So, and then what we can do here is we can say fn run in the child process, and then here we're going to take like the parameter. So the arguments are going to be in the code here, and this is going to be passed in as a parameter. So for this example, we're just going to make, this is completely made up. So I'm just going to make a accumulator function. Basically just grabs numbers in a vec, adds them and returns them. So there's a sum. So this is the sum, and we're going to return basically that. So we're going to return the sum in a tuple and the PID. So we get the child ID using this, then we do the sum using that, and boom, return the sum and the. And the cool thing here is that this is happening in a child process. So we haven't copied this to clipboard yet, so we're going to do copy PID child to clipboard. So we will do this in a minute, but let us get the other scaffolding ready so we can test it out. So let's do this. We can say these are my arguments of vec I64, and let's say we're gonna do we're gonna get the builder, then we're gonna spawn, and we're gonna spawn the args, and here we need to pass a closure, and for that closure I'm just gonna call run child and process. And then I'm not gonna, so if I do this one liner, what it'll do is that it'll execute this and give me the results. But I actually also, because I have actually this will work. So here we have let's see, sum and the child PID. We can then just do this. And println child PID and sum. There we go. Let's see if this works. We haven't copied anything yet, but this is just to let's see if this we can get this much working. And here we see the parent PID is this, the child PID is not that, it's some other number, and then we see the sum. So this is cool. So because we're just suppressing the output, what we can do here is, this is just a copied and pasted code to basically when we did the copy, actually let's do this. Let's do this. Clipboard. Let's do this. Let's update this real quick so that it's just a chunk that I can copy and paste. And there we go. And this can be the same exact thing that's here. Okay. So child PID is not a thing. We do PID child. And so now if we check the contents of our clipboard, it should be copied. So let's run this and see what happens. So let's say, I think this is procspawn. So we get parent PID, child PID, and then let's see what our clipboard has. Oh, that did not work. Our clipboard did not have that in it. Let's see. Why not? Let's run this and see what happens. Oh, it's not actually copying it. So maybe let's see, what do we have to do here? So let me just basically this child process isn't running this one. So we did get builder, we did spawn, we passed it the args, wait, it is running because I saw the output. So we did these. Oh yeah, no, I'm sorry. This is works. So we can do assertions here. We can say assert equals sum is 10, and that should work. Okay, so that did work. So we actually we did get the sum back, and we do get the PID, the child PID back, but for some reason this code is not working. I wonder why. Let's see. So we got child PID. No, PID child. Okay. Okay, let's see if this works. 7, 8. Let me see again. Procspawn. Okay, let's run this again. Oh, okay, now it's working. I wonder what the difference was. Maybe this looks almost exactly the same, so I'm not really sure. Anyway, let me run this again. So when you run this, and then what I'm doing here is I'm just here. I'll show you. Is it presentation mode? Yeah, when I do screencast, you'll be able to see my keyboard shortcut. So I pressed enter, and then here I will say echo, and then paste. So Control V, and then that pasted the 750262. So because it was in the clipboard, so that actually totally worked. So this works. So what we can do is we can even do something like this. We can say let a child, and we can just say parse U32. So this will give us the PID child. So yeah, this is just returning whatever child PID. So maybe what we can do is this PID child from clipboard. So we can do something like this. PID child. So we have to ensure that the PID child from clipboard is the same as PID child. So here we can do clipboard, also U32. So now when we look at usages of this function, we should be able to see here. And these should be the same. Our assertion should be that they're the same. So we can just say child PID sum. We can say PID from clip, and then that should be the same. And assertion should be that they are the same. Okay. It's a bit redundant because there we go. We ran that thing and the assertion failed. But oh, I think I screwed up. It's a bit child. That's why it's failed. Okay, let's run this again. All right, that works. So now if I say paste it from clipboard, you'll see it's the same. Okay, so that totally works. Let me toggle screencast. So there we go. So there you have it. We have this whole thing running. Let me just save this as the code. I will push this into the repo as well. It's actually a pretty good example because we have the because if you noticed, when we run this program, you don't see that warning anymore. So when we say cargo run bin receive signal, you'll see this warning. See this warning? That's the thing that I was wanting to get rid of. And then now when I say cargo run -- bin procspawn, boom, no warning. So that totally worked. So this will end up becoming our procspawn, our first procspawn example. I have one more because signals are because we did an example with signals where we're receiving signals. This is asynchronously inside of our async main function. All of this is happening asynchronously, and this is happening on a separate process, but it's synchronous. No Tokio here. And so the reason we were even creating this function to receive a signal is that signals are a way to do inter-process communication. Basically have the operating system or other processes send signals back and forth to essentially processes that are running so they can coordinate their efforts with each other. So procspawn is just a way to sort of, I mean, this is not really anything to do with signals. This was just so we could spawn another process where we could run some code in a closure, but then we can also suppress, like let's say in our case, standard error. We could have also suppressed, to be quite honest, we can also do this because I don't see why we need to, so we can suppress standard out as well. And standard out, that's null. So we're suppressing those things. So here, in this example, even though this isn't related to signals, we are actually spawning another process. So I'm going to do two more examples next, and one of them is going to receive signals as well as send them asynchronously, and another one will use a full-blown IPC channel to have two processes communicated with each other using procspawn. So kind of showing like async sync, async sync, so just so that it kind of makes sense that you can do it a multitude of ways. One thing I actually noticed while looking at these examples is that there is a lot of use of the unwrap method. So I generally like not to use it, so let's actually go through before going to any other examples, just clean that up. So we're in that receive signal example that we did first, and here we can see all the unwraps. There they are. So here, and quite simply, I could just do, normally I would just do like into diagnostic like that, but this doesn't work. I don't think there's a implementation for me to support the report type. So here we can just instead just do something like just do, actually let me get rid of this. Just say map error, and here we can just say we can just use the met macro, and we can say something like that. But instead of just error, we can say, you know, could not create clipboard context or something like that. And then here we have another unwrap. So here we can just do could not set clipboard contents, and here we can just do wonder why it's parsing to 32. Can just do like this. Yeah, could not get. So actually, I don't think we're doing anything with the item that we get. So this is the copy that we get from the clipboard. Yeah, this is not really doing anything with this. Okay, so actually, whatever we set, we can actually do an assertion here. We can say assert EQ that the paid to string, because that's the thing that I think was originally set. We can just say that equals the copy, like that. And that should work. Let's run it and see. Yeah, it works. We get that strange error message, but that's okay. And let's see if that actually, yeah, I put it in the clipboard I saw. So, okay. I mean, if we run it, we can see it like this. Receive signal, and then there's what's in the clipboard. Something ending in 10, something ending in 10. So that works. Okay, so this is good. Then let me just commit this real quick, and I think procspawn, this one is going to be a little bit more tricky because this is the kind of the nature of procspawn, because the this function, even it's running in a separate process, and it needs to serialize the arguments. So these are serialized or serializable. SERDI. I'm just gonna put SERDI. And this also needs to be SERDiable. And the problem with just simply returning a result, like what we did with the unwrap, or sorry, an error, is that those errors are not serializable. So, because they have a boxed in, they basically use this thing. Where is it? It's in here somewhere. Here's, what is this? I think it's like boxed in error, that one, yeah. So these are not serializable because, yeah, because we have type erasure and we don't even know what we're serializing. So for that, what we can do is, so this is another article on Rust error handling with Miet, where I have an example of using this error crate. So let's do that. So here, what we need to do is bring in both SERDI and the this error crate, because we're going to be using that in a minute. And so here, another thing we need to do is we need to make our own arrow type, because the standard stuff is not serializable. So just looking at this as an example, where is it? Database error. Yeah, right there. Using this as an example, we can just do something like this, where we have an error type called clipboard error, and then it supports, you can derive the deserialize, serialize, and you can derive it as an error. So this error is really nice. It makes it trivial. Oops, not database corrupted. This is clipboard unavailable. There we go. So basically, we're unable to get the clipboard context, and let's see. Oh, lots of spelling mistakes. So here we can do, okay, so now that we have this error type, let's clean up our result here. So here we're going to return a result, but here I'm going to have it return a concrete error. So the clipboard error, and this clipboard error is serializable, so it should be able to, it should be permeable between process boundaries. So this whole thing is this thing. And let's see, this is also serializable. SERDI. There we go. yeah, and so this is the tuple, that's the result, and this is the, I'm sorry, this is the OK variant, and this is the error variant. So this is also serializable. Okay. All right, so those are our, this is the SERDI, this is the OK variant, and this is the variant. Okay. So now what we should be able to do is, with all this done, so this is, okay, so instead of saying unwrap, what we want to do here is we want to do the same thing as before, like map error, but we're just going to map error to context unavailable. Here we're going to map error to set contents, and here we are going to, actually, I'm not going to do this parse thing. We're just going to map error to get contents, and this actually is going to be a string now. So this is no longer U32, this is a string. Okay, so far so good in the sense that, you know, this side of the equation is working. So now this is gonna be like, okay, it's mismatched. And so here what we want to do is we want to say, actually, I wonder if we can just do this. Okay, me at results, and here we just do okay. And import this from Rebel. So, okay. I mean, this is still not, this is still going to be problematic because if we were to kind of look inside of what this is, let's just put this in comments for now. So here you can see it's a result containing a tuple. So, oh, because it's unwrap. We don't want to use unwraps. Let's get rid of that. And now we have a result containing a result. So I wonder if we can just say into diagnostic. Okay, so that, you know, unwraps it once. I wonder if we can do that twice. Yeah. And now we can bring back this thing. And then we can bring back these things. And this is not going to work because this is a U32 and that's a string, so not a problem. We can just say toString. Honestly, it's just to kind of be cleaner. Let's just clean it up here. Let's just make this a string. And here, what we can do is just say PID toString. ToOwned also works, the same thing. Now we have, that's already a string. If we run this, ta-da, it works. So there you go. That was the slightly complicated process of getting rid of unwrap. Simply because, again, this function is executed, if you want to think about it, across process boundaries. So whatever goes in has to be serializable. Whatever comes out has to be serializable. And boxed in error is not just type erasure, so we don't know what the type exactly is, so except that it implements the error trait. So here, by replacing the concrete type, we can do this. So, all right, okay. Now that we started working with the procspawn crate, I think the next example is going to be all about how to use interprocess communication using procspawn. So, and then after that, I'll do another example where we come back to the receive signal crate where we were using async rest to send to receive signals using Tokio, but this time we'll be sending and receiving signals. So essentially, it's these four examples amount to doing IPC and Rust in different ways by spawning multiple processes or by using a single process that's using Tokio, using a variety of different crates and also POSIX signals. So for this next one, let's do this. Let us make a new binary. So this one is going to be called, figured I'd do this one first because we're already looking at procspawn. Might as well wrap that thread up and then move back to the sending and receiving signals asynchronously. So now that we have that, we need to make this file. Let's do this. Okay. and then we need a main function, and that main function is going to return like that. Yeah. All right, so let's add some docs to the top. Yeah, so roughly this is what we're going to be using. This is the IPC channel. It's a different crate. It's not procspawn, but procspawn actually works pretty well with this trait. So if we go to spawn, actually, let's look at the main docs. IPC channel. There you go. So spawn can pass arbitrary serializable data, including IPC senders and receivers. So it's kind of fascinating because we had, I think, in this example, did we send anything? Yeah, we just sent a vec of I64s, which was serializable, but now we're going to be sending actually IPC channel senders and receivers to this spawn process, which is pretty cool. And that's this crate. It's the IPC channel crate. So I think it's only available for Mac and Linux at this point. Yeah. So pretty cool stuff. So it's kind of similar to the channels that we're used to with the standard library and also Tokio. Very similar kind of thing. You make a channel, you get a tuple, extract the sender and destructor the sender and the receiver out of it, and then use it. So to get started, let's do this. So let's make our channel. So what we're going to do is that we're going to, in this one, the previous one, we just spawned a process and a child process using procspawn, and then we basically muted the standard error and the standard out. That's roughly what we did. And then in that process, we copied something to the clipboard because it was generating a warning to standard error and didn't give us a way to turn it off. So this one is going to be a little bit different. Here we're not going to do that copy. We're not going to deal with the clipboard, but we are going to have a way for a very similar to what we do with this stuff. If you look at let's see, developer live. Let's do async. This one. If you look at my video or read the article on the common async patterns for event loops, it's very. It'll look almost exactly like this code, like the spine or the organization of it is near identical. So the first thing we do is we're going to create a channel. We're going to create a parent. So in the parent process, we're going to create a channel. Then we're going to create a child process, and then we're going to take the receiver of the channel and give it to the child, and then from the parent we're gonna send messages to this receiver, and then the receiver, basically the child process, not a task, a Tokio task, but a child process in its own loop, let's say, will pick that up, do a bunch of stuff to it, and then when we're done sending these messages from the parent to the child, then we'll send a message to the child process to terminate itself. So very similar to this. And if you watch this video, it goes into a great amount of details, but kind of showcasing these patterns. Okay, so let's make a channel. So we're gonna create a channel to send messages across. That's this different thing here is that these messages are spawning processes. So we're gonna say IPC, let's see, channel IPC and then channel. Basically, it's this thing. And then this, okay, so this one we're gonna say, let's do this. Let's see what type we get. It's not gonna work. Oh, it's a result. So we're gonna into diagnosing it using niet and return in case that doesn't. Okay, so it's saying, okay, what kind of channel? You know, what is the payload type and so on. So we could do something like, we can say string. And because, I don't know, just so that in case we want to swap out string later with some other type, maybe we can just say message. And then here we can say sender and receiver. Okay, there we go. So there you have it. We have our sender and receiver. So let's see. Let's do this. And then let's see. Oh, and I forgot to, because we're dealing with procspawn. We have to put this line of code here. Actually, no, we have to put it here. So, yeah, because we don't need every single process to execute this, I think. I think so. All right, so we can come back to this, see if this works. I'm not quite sure where to put the procspawn in it, because it says that the spawn process will execute every line of code up to this point. So when the child process is spawned, do I need to create the channel for the child process? Probably not. So this makes sense. So this is like, we don't need, this is good. Okay, yeah, the way I'm thinking about this is like in a test where it's like before each or before all. I think that's how I'm gonna think about this. Okay, so let's see. It's kind of like before. Okay, and then okay, so we made the channel. Then we need to just like we did before. I think we need to make a builder. So we're gonna do create builder for spawning processes. So it's gonna be get builder, and we're gonna do let's see. And this one actually, I want to let's see. I want to pipe it standard input. So we're gonna do something a little bit different here, and read from its standard input. I'm sorry, standard output. And then we can do return it, okay, and this is gonna be mutable. So here, actually, we're gonna do create a builder with standard out piped. That's it. And standard air muted. So that's the thing. So and standard air muted. Okay. So now we can do it dot standard out. We did standard out. We gotta do standard air is muted. Okay, perfect. Because the reason we're making the builder first, because we gotta make the builder and then we gotta call spawn on it. So we gotta make the process builder and then spawn, like we saw in procspawn. So it's just a procspawn thing. Where'd it go? This one. Make a builder and then call spawn on it. So that's the builder. And in the builder, we get to customize our process, the child process, the way we want. Okay, so the next we're going to need a function to run in the child process. So we can say in child process, and it's not going to be vec this time. This time it's going to be a sender whose type is this thing, IPC sender. So we're going to say IPC channel, IPC, and IPC sender. And actually this one is going to be of type message. Yeah, and let's see, message, and then we can do, what is it going to return? Let's just have it return a result for now. And let's see, what is, let's see. use this? So this is interesting because the result is going to be on the, oh, I'm sorry, this is not correct. This is going to be, we're not going to return anything because let me just remove this. We're not going to return anything because we're actually going to write to the standard out. That's why we piped it, so that we're going to use standard out as a way to carry output from this process and deal with it in the parent process. So, and this is not the sender, this is going to be the receiver. I totally, it's easy to get this messed up. Receiver, there we go. Okay, so this one, this runs in the child process. This is this function that executes child process. It gets let's say messages. Where is this? Oh, from the parent process and processes them. That's exactly right. So let's see, we got to do this. Let's see. Okay, and so we know that it's going to be using standard out. So what I want to do when it's finished processing, let's make some constants. So I want it to generate a message. There we go. Basically, when it's done, so basically we can say, yeah, loop until, and then we want to say, that's exactly right. And here we can say print line, something along these lines. So, but instead of these superfluous, there we go. So basically we're saying that, actually let's not do unwrap, let's do this, say ditch the unwrap, and we can say if let okay message, let's do, oops, let's do this block, and then else, actually let me break, and we just basically dump the message, and here we say if it's okay. So basically if there's an error, we don't do anything. We can, I guess we could say else break. So doesn't like it. Oh, really? Okay. Write it as a while let loop. Well, write it then. No. Interesting. I don't know why it doesn't auto-complete this or refactor this for me. Okay. And then we can get rid of this. Oh, that's handy. So while we're getting okay messages, we do this, and then when we start getting errors, we just break out of the loop. So, and now I don't think we even need the loop, because, okay. You know what, I'm gonna rev this back to where it was. I find this syntax a little bit more readable. And if I wanted to, we can just do this match, and then here, what happens? I guess we break, but that's redundant. So let's just go back and leave it the way it was. I think this is fine. That means that as soon as we encounter an error variant, we exit the loop. So, okay. And then we send an end message to the parent process, and I think that's what this looks like. And I think we're good. So this is, yeah, so the function will be executed in the child process, and okay, cool. All right, and so now we have the thing, so we'll get the builder, we'll spawn this function in a separate process. So let's kind of hook that up now. So let's see. So here we're going to do, yeah, spawn a child process and send messages to it. Let's do this. So this one we're going to get, actually when we say get builder and, let's see, we do spawn receiver. That's right, we sent a receiver because it's going to be blocking on that receiver. And then as messages come in, it's going to process them. So that's what this is. We haven't sent any messages yet, so we can put it in here, say to do send messages, and then to do read the standard out, the child process. Okay, so, okay, let's see what this returns. So I tend to put like let equals just to see what it's going to be giving back to me, and I don't want to join here because I have other plans for this thing, so I am just going to do this. Join would basically run it equally. I just want the join handle because I want to get it standard out, and also I want to do a bunch of stuff with it. I don't want to wait for it to exit yet, so here we can say make assertions, and then here we can just shut it all down. So basically to do wait for child process to finish. Okay, so this should kind of start to look familiar now. Like whenever we have like a Tokio, using Tokio, if we have a main event loop where we're asynchronously running in this loop, and then we have a Tokio select block, and then we're basically waiting on keyboard input or network events that are coming in. This is kind of like that, except we control the sender end. So we're going to be manually sending messages. We're not waiting for some external thing. The parent process is going to be the thing that's going to be the source, let's say, of the messages, and the child process is going to be the sink. So let's call this join handle, and this is going to be mutable. All right, cool. So far, so good. So we got a join handle, which gets, okay, unit type, which is as expected, because this is not returning anything. This is this thing doesn't return anything, so it's compiling. Types are happy, so that's good. So now, okay, so this one is, actually that's some documentation there real quick. I don't like this, leaving this blank. I think this is a little bit better. So here we are saying that we're getting the builder and then spawning with the receiver. Yeah, okay, that sounds good. Okay. Let's see, then let's see. Okay, then we have to send messages. Let's see. So before we get too far, let's see if we can get this code to run. So we have the join handle created, which creates the builder that gives us a child process, and then we can run this function in the child process and then send the receiver to it. So I think if we run this, let's see, might actually, let's do this. Let's just do the join handle, wait for it to finish, and let's see, will it finish? It won't, because it's in a loop, so that's not going to work. Okay, so maybe we need to send some messages first before we can test it, or we can take out this this thing. But okay, so let's do send messages. Let's see, send messages, and we're going to send messages via the sender. So let's see if we can. Okay, let's see. That's right, the sender, and then I don't think. Let's see, what are we going to return from this? Just do me for now. Okay. So let's see. So maybe what we should do here is just, let's see if we have a bunch of constants for what messages to send. We do not. Let's make a bunch of constants. So we have end message, shutdown message. Let's make two other messages, message 1 and message 2, and then we'll just, really without thinking, just send these messages over. So let's say sender message 1, then we'll say sender message 2, and then we can say this one actually that's exactly right, shutdown message. Wow, very cool. And this one, I don't think, what happened? Where did the, yeah, we don't need a semicolon for this one. So I think that should work. Let's see, me at result with unit type. Okay, very cool. All right, so now if we send messages, what'll, okay, so let's see, what is this complaining about? Oh, that's fine. So we haven't read anything from the standard out of our child process. So we make a new process builder, we send it to receiver, then the function to run in that process, and then we send a bunch of messages. Okay, cool. I think this should work because, yeah, let me see. Let's run this and see what happens. Where's the run? There we go. Okay, so it did crash, it didn't hang up, so that's good news. So I think so far so good. So obviously now we need to see if actually anything that was intended actually occurred. So we did the send messages, that's great. Let's see, so we have to read the standard of this. Okay, so this, what we probably need to do is, let's make a mutable buffer, which will hold the, whatever comes out of the standard out. So then we also actually need to do this. This is to, what is it called? We need to import the read trait because we're going to use it in just a second. So let's say we have, actually let's do this. We do join, this is how we get the standard out, by the way. We get the join handle using, there we go. That will give us the standard out from the join handle, and it's optional. So what we should do is, can we do unwrap? I never remember how to do this. Like, no, that's not it. Unwrap, or maybe it's unwrap or else that I'm thinking about. Let's see. Nope. Okay. We can just do this. Since we can't really do anything if we can't get the standard out from it, so we're just going to say we're going to use a let else statement, which is pretty awesome. So here we can just say, actually there's a bail function from the yet, which is kind of funny. So here we can say fail to get standard out, something like that. Yeah, bail is it's pretty cool. It's like if essentially like you want to return an error, so instead of saying like return and then actually let me see, instead of doing something like that, you can just do this. Yeah, oops, what the heck, why isn't this compiling? Return, oh right, because that's a, there we go. What the heck, there we go. So this is, I think this is a lot nicer than that. So it just expands to the same thing, just a syntactic sugar. And then we can do bytes read, and then, yeah, that's right. So basically, we create a buffer, a mutable buffer, and then we get the standard out from the join handle, which we get from spawning this function on another process. And then before we exit, we want to basically drain the standard out and then see what we have. So here we want to make an assertion. So here we can say, actually this one is correct. So this one actually, what's happening here is that the read to string, what this does is that it basically drains the standard out, and when it gets end of file, it finishes. So that's what this does. And so when we're generating right here in the child process, these are generating output basically to actually it's not to the parent process, to standard out, and this one is print message standard out, and this is print end message standard out. Oops, what the heck? Yeah, so that's what we're doing here, is we're printing the we're using the standard out as a way to buffer output. It's what we're using to get the return. What, like before, we literally just had the child process return a value. Now we're actually just having the child process write the standard out, and then we can drain that standard out into a string and then make an assertion against it. So here we can say, let's see, assert, I think that's about right, message 1, message 2, end message, because yeah, that's what we're expecting. And then here we can just say wait for the child process to finish. Let's see and run it. Very uneventful, and it worked. So yay. So if we print the, actually here we can do this, we can say println, so the output from child process is that the bytes read is that. I mean, we could do this, it's not really. There we go. Let's run it and see it. There you go. Output from a child process. Actually, let's do this because I don't want to see the carriage return line feeds expanded. And so maybe we could, yeah, there we go. So output from child process is hello, new line, world, new line, end, new line, and then bytes read as 16. So it works. So we can just save that here. Perfect. So with that, this is our IPC channel working. So actually this is it really Git builder? This is basically, it is actually. It's like more like configure builder. Yeah, like because we want to configure it the way we want to use it, with all the muting of standard in and standard out, whatever else we're doing. So let's do this also. I'll make this update in the repo. I think we have configure builder. Okay, I like that. That's cool. And then, yeah, so we have a parent process, we have a child process, and the parent process spawns the child process, and they communicate with each other via this IPC channel. And so the sender and the receiver, we extract that from the channel. The parent actually, let's see, here's the parent. So this is using the, actually, maybe I should just say this, parent send messages, and this one is in the child. We are actually, let's see, parent send messages. So parent sends messages, and the child essentially grabs those messages, prints them to standard out. When it gets a shutdown message, it exits. So this is instead of just using those POSIX signals that we saw earlier, in here we have a much more sophisticated way of handling. So instead of like, you know, sig child, sig cont, so you don't have to, like, we still need to potentially implement those processes, depending on what the use cases might need to respond to those messages or signals. But for processes that we create, we don't necessarily need to use those signals. Those are very sort of low-level POSIX sort of IPC. We can do much more sophisticated IPC here, where we create our own protocol. We can send our own payloads, so it's much more flexible. So with this example done, In the next one, we can basically see how we can create the sender and receiver. So kind of switching gears back to async and dealing with signals. Let's see. So for the final example in this series of examples related to sending and receiving POSIX signals and also creating an IPC channel to explicitly communicate between processes, I think the last bit of work that we need to do, this example I wanted to show, is the other half of this example. So that we have one for receive signal where we're using the Tokio crate to essentially handle signals that are coming from, let's say, Control C or whatever else that are coming from basically the operating system. But we're not actually raising any signals inside of this program. So this process that we create, the main function that's running in that process, like it was merely responding to these signals that were being raised elsewhere. However, for this next example, what I want to show is also for this procspawn example, we weren't raising signals. We were just using an IPC channel, but that spans multiple, that spans across multiple processes. So for this next one, what I want to show is how we can actually not just receive signals, but also send them. And that we can put in here. So basically it's the, actually, let me put this in here for, this is the order in which the things are recorded. So we did procspawn. Yeah, okay. Let me see. There we go. All right, so here we have, we gotta make this thing. So let's do that. We need a new file. And here, let's see, let's write a quick outline of what we want to happen. There we go. So one thing we'll need is, let's see, this is just gonna be a regular main function, I think, not, oh, this is the wrong example. I think the one that I was looking at is this one. Here we go, where it needs an async main function. So there we go. And this is what we're looking for. And we're just gonna stub out OK here. I don't know why it just does this sometimes. The use statement doesn't, I'm not really sure. Let's see, there we go. All right. I wonder what that notification was that just popped up. We found a reference to a public code in a recent suggestion. What does that mean? I don't know. Okay, so let's see. Okay, so we got the stubbed out, and so the crate we're going to be using for this example is where is it? It is signal hook and signal hook Tokio, these things. So that's what's going to allow us to do this send and receive signal, implement the send and receive signal program. Let's see. So what we're going to do here is that we're going to create a main loop using we're going to use Tokio, and you're going to use Tokio select and make a main loop which sits around and waits for signals to be raised. When they're raised, it responds to them. And then, so we're going to have two pieces to this program. One is going to be a task that we spawn which monitors these signals. And there's going to be, just in our main function, we're just going to raise some of these signals, and then we'll see the response. So kind of like this, the procspawn IPC channel, except that this is done without spawning a child process and using Tokio tasks instead. So the main crate we're going to be using for this is this thing. It's the signal hook crate, and we don't necessarily have to use Tokio at all. We could just use signal hook in like entirely. Signal hook also has signal hook Tokio crate, which allows it to nicely integrate with Tokio. So this is basically the what we're going to do is that we're going to actually, this is basically the example. We're just going to create an array of signals that we want to respond to, and then we will basically spawn a task which just grabs this signal stream, which is similar to what we did here, this stream thing, but obviously that was using Tokio, but this is using signal hook Tokio. So and then based on whatever signals are raised, we do something, and then we shut down. So what we are going to do is we're going to have basically two tasks. One is going to listen to these, in a way, the stream of signals, and then we're going to have another task which is running on the current thread of the main function, which will also be in a loop. So basically two tasks, each one is going to be in a loop, and so the main the main loop, the main event loop, it's going to loop until it gets a shutdown signal, and the shutdown signal will be generated by the task that's monitoring the stream, the signal stream. It's a bit contrived, meaning that when a signal comes in, the task that's monitoring the stream of signals, that will then tell the main event loop that, okay, it's time to shut down. And so what we need, the first thing is a broadcast channel. So this is a broadcast channel to shut down the process or something like that. So let's do this. We can say Tokio. For this one, we can just use a broadcast channel because it's easy to send across Tokio spawns. Because what you do is that you just grab the sender, and we don't really care about the receiver, and then we can just subscribe to this thing, and we'll get a receiver out of it. So it's super easy. So this is, we're going to do, let's see, broadcast channel to shut down, yeah, send shutdown signal, and then let's see, then let's register these. Let's listen to some signals, and then we'll make the task that's on the current thread of the main function. So let's do this first. So we're going to register signal handlers, then we're going to do execute main event loop. Let's see, say this will be event loop, and then we will let's see, and I think clean up. So we're gonna clean up everything. Okay, clean up and shut down. Actually, more like clean up after shutdown. Any tasks. So that's the to-dos. So so the first thing we're going to do is just copying it from here, where we have a bunch of signals that we're going to get. So we can do like this. We can say, actually, let's do some imports. Let's do this. Okay, so what we're actually, let's see, use features as, because this is just for some traits that we'll need. So okay, we have the signal stream. So we're interested in sig hop, sig term, sig int, and sig quit. So these are all the array of signals that we're going to respond to, and then like it says here, we gotta do this handle thing. So we can do signals handle is signal stream dot handle, and then now we're gonna create a task. So we're gonna say tokio spawn, and we're gonna do this thing, handle signals task, and we will pass this I think the signal stream, yeah, signal stream, and we're gonna send it this exactly what it auto-completed. So, and this will return a join handle. This is the task that's monitoring monitor signals task basically. And so here what we can do is we can do something like this, join handle, yeah, we just basically await it. That means while this thing is running, we're not going to exit for whatever reason. And then another thing we can do is this terminate this. There's the handle thing that we created. It says to close it, so we're going to do signals handle dot close. There we go. That's our cleanup. So this is to do. We need to do this, and we also need to make this. So let's generate a function for that. So okay, well, that's not very helpful. So the thing that we're going to get, the signal stream, is actually of type signals. So we can just do that, and this clone thing that we're just going to call it, that's a Tokyo sync broadcast sender, and it's just unit type because, you know, that's why. So, and it won't return anything, I don't think. So, and then let's see, why is this red? Oh yeah, of course, this needs to be async. All right, and then now that's happy. Okay, so let's do, let's implement this. So let's say to do implement this. Okay, so so here what we're going to do is that while we can get some signal out of the signals stream, that should be mutable. And I think the signal stream, yeah, okay, that's good. So, oops, sorry. So we do that. So this basically, there we go. And actually, this is not the correct loop, but it doesn't matter. What we want is if it's sighub or sigterm or sigint or sigquit, what we want quite simply is this is actually unreachable. So why is this red? Oh, okay. And then what we want to do here is that, remember we had that this thing, the sender. We want to send unit. So, and then we can just say we don't really care about the result that comes from it, but we just want to send it. I think that returns a result, yeah. So this just basically consumes the result. I like, because we don't want to do this because there's nowhere for this to return to, because this is gonna, it's been spawned. So we just like silently exit basically in case there's a problem. So this takes care of the handle signals task. All right, so that's our task for monitoring the signal stream. We haven't raised any signals yet, so let's do that. So for this one, let's do this. Let's say run main event loop, and here we want the sender shutdown channel. We're going to let's see. So let's make this one. So this is going to be run main event. Okay, there we go. And actually, that's not exactly right, but sort of. Let's call this receiver shutdown channel. So actually, let's just do this. Okay. So, what we'll do is that if let's see, I think it's supposed to be. So when a signal comes in and this task handles it, we will then send something into this shutdown channel. When that shows up here, then we have to break. So here we'll say break out of the loop, and that exits this function, which should come back here and clean up. So what is the problem here? Break outside of loop. Oh, right, this should be a loop. So let's do this. We're gonna put this in a loop. All right. Yeah, it's because we're not really, there's no other branches. So this is the branch that allows us to respond to one of these signals being raised. Currently they're being raised, let's say, external to this process, but we could raise them internally as well. So this is the listening half. Now we can generate the sending half, or the raising half. So what we're going to do is that just so that this runs for some time, let's do an interval. So we're going to do a tick interval that runs every 500 milliseconds. Let's see. Oops. How does this work? Control, right arrow. That didn't work. Control. Right arrow. Okay. I don't know why this is. Okay, let's see. Accept word. Oh, wow, that's tedious. Let's do this. Okay. So we're gonna do from millisecond 500, and we're just gonna print, and we're just gonna keep going. Like, we're not gonna stop. So this will currently just infinitely run for. Let me see. Actually, do we have enough? Let's see. Let's run this and see if it runs. So it's ticking, and if I hit Control C, that killed it. So let's do one thing real quick. Let's also print the PID of this thing. I think we have some code to print the PID. There we go. Let's do that. I guess we could copy to the clipboard too. That'd be handy. So let's do this. Let's call this print PID. And we're going to do fn print PID like that. And that should just work. Okay, let's run this again. I think we call it receive. Nope. This is send and receive signal. What happened here? Oh. Oh. I see. Okay, that should work. I guess we could do this. Print PID. Yeah. What is the problem? Oh, there we go. Okay, let's run this again. There we go. So we have the PID, and I think, yeah, the PID has been copied to the clipboard. I just checked. So excellent. This is going to keep going forever. So we can now use the kill program, or we can use system monitor to send signals to this thing. So let's try that. Let us do this. So basically, we just recreated the first example, but now we're just using this signal hook Tokyo instead of Tokyo. So we can say kill dash int, and why is the PID not ping? Okay, that's weird. This terminal locked up. Okay, let me try this again. So we run this thing, do that. Huh. Very strange. Let's see. That works. So we do send and receive signal. Okay. Okay. That is the weirdest thing. So we can do kill dash int. Really? What's the PID then? 102518. Oh, so the copy and paste is not working. This is so strange. Kill dash int. Oh, I don't know why it's not pasting. Must be some Wayland issue. Like I'm pressing paste here, but nothing is happening. Seems like the input to this thing is frozen. Yep. Okay. Let's try this again. Maybe let's do that. Int, and then let's grab this PID. Okay. So as you can see, that received the shutdown signal, and it did shut down. So yeah, so that works. Okay, so now what we want to do is actually raise this signal in the main event loop, not external to this. Actually, since I wanted to show this real quick, instead of using the kill program, let's try this. So we do send and receive signal. We're looking at PID, this thing. Oops, 125. So let's do this system monitor. Let's look at the PID, that thing right there. And then we can do like this, and we can say raise a signal, raise another signal. Hey, look at that. So we were able to send a signal, and then our handler responded to it. So let's do this again. Let's see what the PID is here. It's that, and then we can do stop. Oh, that actually was a syscall, so we don't. I don't think we can even register a handler for that. But anyway, it's possible to send signals from the. Oh, interesting. That actually paused the program. Interesting. Okay, so that aside, let's just see if we can send the signal here. And in order to do that, what we want to do is we're gonna send a sigterm signal, but we're gonna wait. So wait for 1 second and then send sigterm signal. So the way this would work is that we can just say, and we're gonna like this is pretty silly, but we're just gonna spawn a task to do this. So we're gonna say wait for 1 second, and then we're gonna say signal hook, which is this thing. And if you look at the docs, there's signal hook. What's the name of this function? It's I think raise. Let's see. Let's just do a search. Say raise. There it is. So we're going to use this thing. Signal hook low level raise, and under the hood it actually uses libc and straight up makes a syscall with the Linux kernel. So we can say low level raise, and then the signal that we want to give it is sigterm. And there you go. Actually, why don't we just do this? Yeah. And then we can say print line send. So basically, after 1 second, this will raise its own signal, which will be interpreted. Basically, it's using IPC. It's using POSIX signals. It's just that it's raising the signal asynchronously within the same process. So essentially, it's sending a signal to the operating system, saying, "Hey, operating system, raise a signal on this PID," and then the signal comes in and it handles it itself. In other words, it self-terminates in the strangest way possible using signals, even though the actual shutdown message is transmitted using the broadcast sender or the broadcast channel. Very contrived example, but I just wanted to show how all of these things kind of can be wired together. So in other words, this just self-destructs. So if we run it, it'll just, oh, what the, oh. And I think we have to, yeah, we don't really care what that, we just ignore the result basically, even if it's an error. We're being pretty lazy about error handling. So check this out, tick, 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 boom, done. So it sent the sigterm signal and it received it. So here we can see, maybe we put an emoji. Let's see, what is it, firecracker? Yeah. We send the sigterm signal, and then in this task, I think we receive it. There we can say received a signal, and this one we can say, let's see, what emoji. That's pretty silly. Like we got like an email or something. So like an inbox. Yeah, we'll just say we got an inbox. All right. So we're gonna see, there you go. So there's a task that sent the sigterm signal, waited 1 second, sent it, and then this other task, which was monitoring the signal stream, it got the signal, and then it sent a message over the broadcast channel to the main, this task, and it shut it down. And it also exited itself, basically. So here, we don't have to do anything with shutdown here. Like, technically speaking, we could monitor the shutdown channel, but we don't have to, because if you remember, we did this. So this takes care of it. So there you go. And that's an example of using the signal hook Tokio, which uses signal hook crate to actually manipulate signals in order to interoperate with POSIX operating systems and processes. But yeah, so please take a look. Yeah, we have a Discord, so if you have any questions, thoughts, comments, please do put it on the Discord. And yeah, if you like this video, please give us a thumbs up. It helps me grow the channel. Please subscribe. That way you'll be notified when I release new videos. I think this is the third of a 3-part series. I'm intending to, I think I'm going to publish them all at the same time. And there's a blog post coming on Developer Life. If you haven't already, please go to developerlife.com and subscribe. I usually don't post that often, like maybe 1 to 2 a month. you might get an email. And like, for example, for this video, I will take the blog post and the 3 videos and put it in this, send out an email to the subscribers. But yeah, and the YouTube channel is right here. So there's a whole lot of really good videos here. If you haven't already, please check these out. This particular one is a kind of a deep dive in the TTY space, but you know, there's a whole host of other things that we have in Rust. So right there. And if you have ideas for videos that you want to see, please do share in the Discord. And I think at some point I do want to start a podcast, which is in this channel itself, related to startup topics and things like entrepreneurship, hiring for startups, culture at startups, and just companies in general. And then in terms of the live coding videos, I have another one in the works, which is on lifetimes, so stay tuned to that. Then I have another one on, I think, clap colorization, and I have another one in Ubuntu and keyboard shortcuts. So these are all kind of something to look forward to over the next couple of weeks and maybe a month or 2. Thank you again for watching. I hope this was useful, and yeah, I'll see you in the next one.